The overall goal of a Griggs-type experiment is to explore the deformation processes of rocks at high pressure and temperature, typically higher than 1 gigapascal and 300 degrees Celsius.
The advantage of this technique is that deformation can be applied up to pressures of 5 gigapascals. That corresponds to a depth of approximately 150 kilometers in the Earth. This method can help to answer key questions in geology in the fields of structural geology, geodynamics, magmatic studies, and even planetology.
Here we use a new generation Griggs-type apparatus, which complies with European standards for safety of high-pressure experiments. Based on the piston cylinder technology, it consists of a metallic frame and 2 hydraulic rams connected to actuators and pistons that first pressurize the sample assembly within a pressure vessel and then advance the central piston to deform a sample. In the present video, we show how to perform a Griggs-type experiment using the conventional solid salt sample assembly.
To prepare the sample assembly, first, grind at least 60 grams of sodium chloride powder of 99.9% purity in a ceramic mortar. Then, cold press the salt pieces. To produce the lower outer salt piece, place 17.5 grams of ground sodium chloride powder into a beaker. Add approximately 0.1 milliliter of distilled water and make sure that salt and water are well mixed. Fill the wet salt powder into the borehole of the salt pressing tool and put its piston components on top of the salt powder. Press the powder at 14 tons for 30 seconds and then unload the salt piece. Take out the lower vessel component and move the 2 basal metal pieces apart to leave an empty space below the borehole. Once again, use the piston components and hydraulic press to extract the salt piece from below. After making an S-type thermocouple as described in the text protocol, use a milling machine and the drilling tool to drill a hole of 2 millimeters diameter all through the length of the lower salt piece. At the top of the lower salt piece, use a scalpel with triangular blade and sharp point to carve a small channel of around 1 millimeter deep and 2 millimeters large from the thermocouple hole to the bore. To jacket the sample, use a round-shaped, hollow punch to extract 2 discs of 10 millimeters diameter from a platinum foil of 0.15 millimeters thick. Make 2 platinum cups by bending a 1 millimeter rim of each disc using the cup shaping tool. Then, use a tubing cutter to cut a platinum tube of the length of the sample, plus approximately 3 millimeters. Use a benchtop muffle furnace to anneal the platinum tube and cups for at least 2 hours at 900 degrees Celsius. Once annealed, fit 1 cup into the platinum tube and use a file tool to grind the end of the tube and the cup flat. Then, weld the platinum cup and tube together using the welding tool and a PUK5 welding microscope. Wrap the sample into a nickel foil of 25 micrometers thick and fit them into the platinum tube. Close the tube with the second platinum cup and grind them with the file tool before welding the cup and tube together. Slightly bend the tips of the platinum tube using a pair of flat needle nose micropliers so that the top and bottom alumina pistons can fit as far as possible into the platinum tube. Using the same pair of flat pliers, press the tube onto the alumina pistons all around to maintain a small total diameter. Put together the lower outer salt piece, bottom copper disc, and graphite furnace. Use a permanent pen to mark a dot at the expected position of the thermocouple on the outer paraphyllite sleeve of the furnace. Take the outer salt piece out and insert the inner salt pieces around the pistons and jacket within the graphite furnace. While maintaining the graphite furnace, inner salt pieces, and bottom copper disc together, use the milling machine to drill a hole of approximately 2 millimeters diameter where the position of the thermocouple has been estimated. Next, prepare the lead piece by placing a ceramic recipient containing 50 grams of lead into a benchtop muffle furnace at 400 degrees Celsius for around 30 minutes. When the lead has entirely melted, pour it quickly onto the lead piece tool. And immediately use the 40-ton hydraulic press to press the lead at 4 tons for 30 seconds. After removing the lead piece as before and preparing the sodium chloride insert as described in the text protocol, assemble the 2 pieces together. Put together all pieces that compose the sample assembly except for the top copper disc, lead piece, and packing rings. Wrap the outer salt pieces, lead piece, and base paraffilite piece with Teflon. With the pressure vessel mounted as detailed in the text protocol, leave the vessel suspended as high as possible above the base plate. While carrying the sample assembly, carefully fit the thermocouple into the thermocouple hole of the base plate. Then, put the sample assembly at the center of the base plate. Once in place, add a foil of mylar film in between the base plate and pressure vessel around the assembly. Use the arbor press to carefully lower the pressure vessel onto the base plate and fit the sample assembly into the borehole of the pressure vessel.
When inserting the sample assembly into the pressure vessel, make sure that the mullite sheath of the thermocouple does not break. If it breaks, you may have to replace a large part of the sample assembly.
Then, use adapted clamps to fix the pressure vessel and base plate together tightly. And add the top copper disc, lead piece, and Sigma 3 packing ring on top of the sample assembly. Carry the pressure vessel upside down and put it on a workbench. Slide plastic tubes over each wire of the thermocouple to insulate them from any metal piece. Fix each wire to an S-type universal flat pin thermocouple connector. Bend and fit the wires into the basal groove of the base plate, glue them with tape on the pressure vessel, and put a piece of regular paper sheet between the two wires. Then, turn the pressure vessel into an upright position and place the end load piston, confining piston, and deformation piston with the Sigma 1 packing ring on top of the sample assembly. Place the base plate, pressure vessel, and pistons onto the bottom platen of the new generation Griggs-type apparatus, and plug the thermocouple connector to the temperature regulation system. Prepare the software for the deformation experiment and start the deformation pump as described in the text protocol to advance the deformation actuator. When the deformation actuator is around 3 to 4 millimeters above the deformation piston, stop the pump and move the pressure vessel to align them.
It's important to almost perfectly align the deformation piston with the deformation actuator of the apparatus, otherwise a piston could break during the experiment.
Use the deformation pump to fully lower the deformation, confining, and end load actuators so that they touch the pistons, and start increasing the pressure as described in the text protocol. When the confining pressure is around 50 megapascals, plug the vessel and pistons to the cooling system, and detach the upper part of each clamp that fix the base plate to the pressure vessel. Add a foil of mylar film between the clamps and vessel, and start heating as described in the text protocol. Then, use the hydraulic pumps, heating system, and cooling systems to perform the deformation experiment. After the experiment, when the heating and cooling systems are stopped and the pressure is around 0.5 megapascal, reattach the base plate to the pressure vessel using the adapted clamps. After opening or closing the valves of the apparatus, as described in the text protocol, unplug the thermocouple and tubes of the cooling system for the pressure vessel. Use the hand pump to lift up the confining and end load actuators as much as possible. Start the deformation pump and lift the deformation actuator up a few millimeters more than the confining actuator. Then, take out the vessel and pistons from the new generation Griggs-type apparatus. Remove the deformation, confining, and end load pistons and put the vessel upside down on a workbench. Unscrew the S-type thermocouple connector, remove the isolating plastic tubes, unscrew the clamps, and take the base plate and mylar foil away. Turn the vessel upright and place it on the platform of the hydraulic press to extract the sample assembly from below. Put a piece of lead on top of the Sigma 3 packing ring and use the 40-ton hydraulic press to press out the sample assembly. Finally, carefully dismantle the sample assembly using pliers and a curve cutting edge scalpel. Representative results of Carrara marble deformed at 700 degrees Celsius and 1.5 gigapascals are shown here. This includes a scheme of the deforming sample assembly and the stress versus time curve produced during the deformation experiment. At first, both the pressure and temperature are increased alternatingly during the pumping stage. While the sample assembly is heated by using the Joule effect, both rams transmit forces to actuators and pistons that pressurize the sample assembly. When the target pressure and temperature are achieved, a period of hot pressing is applied to sinter the sample, if applicable. Then, the sigma-1 deformation piston is advanced, moving through the lead, and then pushing on the alumina piston to deform the sample. This describes a hit point followed by an elastic then plastic curve during the deformation stage. When deformation is stopped, the temperature is quickly dropped and the pistons are moved back, so that pressure is slowly decreased to preserve microstructures. After the experiment, the stress versus time curve is corrected from friction and rig stiffness to calculate the total strain and differential stress prior to characterization by analytical techniques. This type of experiment can also be performed with non-coaxial geometry, as shown here, for an olivine aggregate deformed at 900 degrees Celsius and 1.2 gigapascals.
After watching this video, you should have a good understanding of how to perform deformation experiments using the new generation Griggs-type apparatus, particularly to prepare the sample assembly.
Generally, people new to this technique need some experience in preparing the sample assembly and placing it into the pressure vessel in order to secure a good success rate of experiments. Once mastered, this routine usually takes tens of hours, partly because of the curve fitting needed to define the hit point.
It's important to remember that the success of an experiment highly depends on the production quality of the sample assembly. During pumping and quenching, it's also recommended to move pistons as slowly as possible to avoid breaking any metal piece.